Our next speaker is Shankar Sharma, who's a theorist who works in the field of condensed matter and quantum computing. He is a professor of physics and also the director of the Center for Condensed Matter Theory at the University of Maryland. And he's going to tell us about how quantum meets topology, and especially in the context of the quantum Hall effect.
Thank you, Subrata. Good morning, everybody. Thank you very much. I'm very excited to be in this very important conference celebrating 100 years of Heisenberg's famous paper, which very few people understand, the original paper. So what I will take actually a step back from where Philip finished. I'm going to talk about integer quantum Hall effect, which of course is where it all started. Literally, my talk would be quantum meets topology, quantum Hall effect. And it's, I think, a apt topic to talk about for the 100-year anniversary of quantum Hall. Now, if you look at APS journals and just do a simple search and ask the question, how many times did the word topology show up in the title of or title abstract or in the archive, and you'll find of the order of a dozen in the first 100 years of physical review journals. Up to 1980, only about 10 or 12 times. But if you look at it now, it has been like 20,000 times after that. And all of that happened because of quantum Hall effect, okay? So let's start with, perhaps the most fundamental constant in quantum mechanics. For younger generation, I'm using CGS units, okay? Do not talk about vacuum permittivity. I'm going to get very upset, okay? So it's all CGS units, okay? So it's the most fundamental constant probably is fine structure constant. Perhaps Planck's constant, but Planck's energy is just too high. E square H over C. The value is 1 over 137. And in fact, the current base value is this, up to 10 decimal places. And this comes from the G minus 2 measurements of QED. Magnetic moment measurement, anomalous magnetic moment. But now, some of you know, I'm sure, that E, H bar, and C, and meter, kilogram, and second are precisely defined. There is no ambiguity in them. Precisely defined metrologically. This is as of 2020, okay? And vacuum permittivity plays a role there. So then this kind of strange paradox arises that if E square over H bar C is a constant, C is a velocity, then E square over H should be a velocity also occurring in nature, okay? Because it's just obvious right there. And it should also arise physically. After all, C is one of the most physical velocities in the world. It's velocity of photon, okay? And Einstein told us invariant. You need that to make Maxwell's equations invariant, right? So there should be an invariant velocity in nature which arises physically, which should have this value. What is it? And what does this invariant physical velocity alpha c arise in nature? This question actually could have been asked 100 years ago, right? Because alpha is already known, electron-photon interaction. People were already working on QED, maybe not 100 years ago, but certainly, let's say around 1930. You can also see that H over E square, 26,000 kilo ohms, is a natural unit of electrical resistance. H over E square is 26 kilo ohms. Now, when you combine all of this, oh, by the way, in case you did not know this, electrical conductance has exactly the dimension of velocity in CGS unit. Again, no SI units, okay? Because SI unit predates CGS units in some sense. Originally thought that electricity doesn't fall under the paradigm of length, mass, and time, but we know that's not true. This invariant velocity, alpha c over 2 pi, 1 over 26,000 kilo ohm, is the quantum Hall conductance, okay? This is this invariant physical velocity, and it actually occurs in nature. Klaus von Klitzing discovered it in 1980 purely through serendipity, okay? And he saw this resistance, and then he realized it's connected with fine structure constant. And anecdotically, the reason he immediately connected this is because he did all his undergraduate internship in German Bureau of Standards. So he knew that that resistance has this unit, and that is the advantage that he had. So this quantity, why is it invariant? This is the question to ask. Electrical resistance is a macroscopic property. It's a property of 10 to the power 23 electrons doing things together. This is not like velocity of light, or it's not a property of a fundamental particle. Why should it be invariant? In solid state physics, nothing is invariant. We are filled with disorder, dirt, contacts. These systems are very bad, okay? Nothing should be invariant. No two sets of data, even for identical physics, are ever the same. In fact, no two sets of data and the same sample are ever the same. Ask Philip. They're statistically the same, but they're not identical. Invariant things simply don't happen. This is invariant because of topology, okay? And so all the conductance is the macroscopic property of 10 to the 23 electrons. Topology imposes a constraint which makes it invariant. And this is what I want to talk about. So this is the original experiment of Klaus von Klitzing, now a legendary measurement. The title was New Method for High Accuracy Determination of the Fine Structure Constant Based on Quantized Hall Resistance. This is his data, where he's showing is just Hall and longitudinal conductance. So in some sense, this measurement could have been done by Mr. Hall himself in 1878 if he had access to two-dimensional system. And this is one of the figures. This one is the Hall resistance. And you see it's going down because it's increasing density. And this is the longitudinal conductance, okay? And what you see is that wherever the longitudinal conductance vanishes, the Hall conductance or Hall resistance is quantized, okay? Wherever it vanishes, this is 0 here, quantization. And he measured the value, and he found that it's h over 4 e squared. This factor of 4 comes from spin and value. Don't worry about it, okay? The important thing, the unit is h over e squared. And he saw that this actually is constant, one part in 10 to the power 5. I actually asked him how he realized it's a constant. And he said, he was using the same current. And then he told me that when you see night after night, the XY recorder, this is pre-computer, XY recorder, the pen is going along the same line forever, so the paper is getting torn, you realize something is going on. So this is a direct quote from him, okay? So then he looked at the resistance and immediately realized it's quantized in h over e squared because of his standard background. This is result of Sui and Stormer in gallium arsenide. Here, the quantity one is changing is magnetic field. You can change filling either by changing magnetic field at constant density or changing density at constant magnetic field. Here, you can see the plateaus very clearly. This is just 2 years after this measurement, plateaus very clearly. And again, you see wherever the longitudinal resistance is 0, you have plateaus, and these plateaus are quantized in those units. So classically, what would it look like? Classically, the resistance is just going to be linear. It will just increase linearly. B divided by NEC, formula derived by Mr. Hall in 1878. In fact, why Hall came up with Hall effect for this talk, I did some studies, also very interesting anecdotally. Maxwell made a mistake in his paper, actually. And he made some incorrect measurements of what transport would look like in the presence of a magnetic field. And Hall, who was a young graduate student in Johns Hopkins, realized that there is a mistake. So he went ahead and measured and corrected the mistake by great Maxwell. And this is what the quantum looks like. So classically, it's linear, and this is like constant. Quantum, it's quantized. And now we know this value of this resistance, sometimes called von Klitzing constant, is defined. Now resistance is defined. You don't have an ohm in Gaithersburg or in Germany or in Paris anymore. It's a precise value. This is the number, and anybody in the world can just measure this. This is the value. And now notice, alpha is measured accurately 10 decimal places. There is another story here. Klaus von Klitzing named his paper originally accurate the new resistance standard based on quantum Hall resistance. The paper went to Barry Taylor at NIST, who is in charge of standards for the whole United States. Barry Taylor accepted the paper by saying you have to change the title because resistance is our standard resistance, this kind of a weight of platinum we have in oil, that's precise up to 6 decimal places. Your thing is precise only up to 5 decimal places. So change the name to accurate determination of fine structure constant. But that turned out to be incorrect because QED still measured this better. So in any case, this is, the title was changed, but the rest is history. And I already told you what's going on. So the rho xy, which is given by B divided by NEC in 2 dimension, the system is divided into Landau levels, and each Landau level has a macroscopic degeneracy. And so when you combine this macroscopic degeneracy, the Landau length, you immediately get the formula that resistance is h over nu e squared. So you may say, what's the big deal? Classical formula is already giving me this thing is quantized. The problem is this thing is quantized as a set of measures 0. This is telling you that at some points along this rho xy, this value exists. This is not very helpful, okay? That at some precise point, there is no, it's not telling you there should be a plateau. The important thing here is not this value. The important thing is that there's a plateau precisely at this value whenever you feel an, integer number of Landau levels. Question now is there lots of different things come in. Why is this thing a constant in the presence of disorder, temperature? That's what basically what topology will tell us. So this is a picture of the notebook that Klaus von Klitzing, you see the time, 2 a.m. This is the precise time of the discovery of quantum Hall effect. So this is, so you can see, this is the resistance. This is the same figure as this, exactly the same figure, but here is the classical Hall formula. This is what classical would look like, and this is the longitudinal resistance, and this is what it is. All right. Now you'd say, well, this looks like it should have been predicted, and it was kind of predicted. There is a paper in 1975 by very famous Japanese theorists at that time. I'm not putting anybody's name on anything. Now look at what it says. It calculates these diagrams. The goal of the paper, it's a very long paper, goal of this diagram was a many-body calculation of the Hall resistance in the presence of a strong magnetic field in 2 dimensions. So what they wanted to calculate is a correction to the classical formula because of electron impurity scattering. And so they calculate a set of leading order diagrams. We know what the leading order diagrams are. You can write them down obeying word identity. And then it says, this means that electrons which fully occupy impurity bands do not contribute to the Hall current, while those which occupy the main Landau level give rise to the same Hall current as that obtained all the electrons of the Landau level are full. So it's an effective prediction that the electrons that are localized would not contribute, but the rest of the electrons go faster and contribute to Hall resistance. You say, well, great, it was a prediction. Why isn't it that immediately people did not start doing experiments? And there is the next sentence. Next sentence is, this is what the theorist, the next sentence is that effects of higher order bond scattering make this effect go away. Because they did not think in terms of topology, okay? Because if in the gap, you're protected by the gap. So it's a very sad story. I mean, Sune Ondo, very, very smart guy, came this close to predicting, but he believed in many-body calculations. I'm that way too. I'm very suspicious of very general abstract arguments. Usually they don't work in solid-state physics. Something kills you. But here is a case where it works. Then just after this effect was seen, my colleague Dick Prange, my late colleague Dick Prange showed that if you take a two-dimensional electron gas, add 1 delta function impurity to it, then exactly have 1 bounce. It's an undergraduate quantum mechanics problem. You just write down the Schrodinger equation, put 1 impurity, then it binds exactly 1 electron. And then you calculate the current, you find, yes, 1 unit of current is less because there's 1 bounce state, but the rest of the electrons goes exactly faster to compensate for this current. And if you put 10 impurities, same effect. So there was something magical. This cancellation takes place. Laughlin came up with the first topological argument, although Laughlin did not call it a topological argument. He called it a gauge argument. He said, let's make the two-dimensional thing into a ring, and let's add an additional flux through it, okay, through the hole. So this is very much like Aronoff-Bohm type idea. Now, if I change this flux by 1 unit, I have not done anything. So electrons must map back onto themselves. So what can happen? Only thing that can happen is a finite number of electrons moving from one edge to the other. Since a finite number, Hall effect must be quantized. This argument says disorder, nothing can do anything by this argument. So this is kind of dependent on edge current, Stokes theorem, gauge invariance, adiabaticity. He did not use the word topology, but it really is a topological argument. Thouless first calculated the quantity, this Hall resistance, using Kubo formula, and he actually wrote down what the resistance, what the quantity would look like, and he found that sigma xy, sigma xy has this form. Sigma xy is constants times c, and c is an integral. And he wrote down what that integral is. This integral is this form, and this is what we now call Berry connection. Thouless did not call it that because Berry's paper hasn't come out yet. Okay? It's still with the referees or something like that. And Thouless then showed that this thing, if your Fermi level is in a gap, this thing will be quantized. It's just, there's no effect of disorder or anything. It's exact, okay? So, and he said that, okay, so it's quantized. But he did not actually come up with the word Chern number. That Barry Simon, and I just learned from Professor Berry that they were in a conference together in Australia, and Professor Berry gave Barry Simon his paper, and Barry Simon said, oh, now I understand what Thouless is talking about. This is nothing other than the first Chern number. This is the first use of the explicit word Chern number in physics. Now, Young had things in the context of Young-Mills, the gauge theory, topology and Chern class, but the word Chern number first appeared in this Barry Simon paper in the context of how Thouless explained quantum Hall effect. Then, of course, Chern-Simons theory is the effective field theory, which we theorists think is the theory for quantum Hall effect. So Chern-Simon theory is a zero-parameter theory. Zero-parameter theories are incredibly good and incredibly bad. They're incredibly good because they explain something completely. They're incredibly bad because they have no predictive power. They have zero parameter. So the Chern-Simons theory immediately explains why. So you write down the Chern-Simons action. There is this parameter K. K has to be quantized here, constant here. K can be only some number. It immediately shows that the thing is quantized. But the fact that disorder is essential for this, because you need these localized states, you need to be in a place which is in a gap, that's just hidden in this whole thing. So Chern-Simons theory says that the t is equal to 0, all these topological theories say t is equal to 0, quantum Hall effect is Chern invariant, but they're useless experimentally, because experiments do not take place at 0 temperature, and it doesn't tell you the correction to quantum Hall effect is. It tells you the resistance is precisely quantized in an infinite system at t is equal to 0 for very weak disorder, as long as the chemical potential is in a gap. But it does not tell you anything about why there should be a gap, why the chemical potential should go continuously rather than jump from one level to another. So although it explains the quantization, it cannot do anything else. So one integer quantum Hall is a topological phase protected by a gap and characterized by the Chern number invariant. This is the first prototypical example of what we call symmetry protected topological phase in physics, and also the decisive one. By decisive, I mean where the quantization has been precisely seen. But Chern-Simons theory, while asserting this is guaranteed by topology, it says nothing about its experimental observability at finite temperature and disorder. In fact, if you take all these theories literally, there is no quantum Hall effect at finite temperature because it's a topological effect at 0 temperature. So the gap is a topological protection. The theory explains quantization after the fact, but does not predict it. It does not tell you how to calculate any correction. And we have to be able to calculate, as Juan Maldacena was telling us this morning, and that's where you need a microscopic theory. Now, let me tell you that you may think I'm telling you obvious things, but we are extremely lucky that the gap is large here. Imagine if electron mass was like 100 times, the effective mass here was 100 times the electron mass, all these gaps would be very, very small. This is what Philip was talking about. All these gaps was 1 millikelvin. All the topological arguments will be exactly the same. Topology will still predict this effect, but nobody will ever see it because you'll have to go to microkelvin to see it. So all these details matter in solid state. So abstract theory may tell you something should happen. It will not happen, but the fact that the gap is large is purely accidental. No theory tells you the gaps has to be large. And you know, I know that hard way because we predicted existence of Merner zero mode in this in certain system, very complicated system, nanowire on a superconductor magnetic field, and a certain company is spending hundreds of millions of dollars trying to realize that in lab. Hundreds of people are working on it, but it's not clear that Merner zero mode, which is some quantized object, the quantization here is a Pfaffian, not a Chern invariant. It has been seen. Why? Because the gaps are very small. Gaps are of the order of 100 millikelvin. So seeing it is very, very difficult. This prediction is as pristine as the prediction of, it's same theory, same kind of field theory, okay? Some kind of topological quantum field theory. So the predictions are identical, but here seeing it is very difficult because the gaps are small. Okay, if this happens, by the way, that will lead to topological quantum computer. So, for example, the people who work on standards have measured the correction to, experimentally measured. This is, for example, the correction to the quantum Hall resistance because of system size. You see, these are all quantum, these are Hall bars of different widths. This is how the correction to rho xy, the deviation from quantization, varies with the finite value of rho xx. Remember, rho xy is exactly quantized when rho xx is 0. And again, Chern-Simons theory doesn't tell us if I give Mr. Chern-Simons theory or Miss Chern-Simons theory a value of rho xx, it has no way to tell me what rho xy would be. But that has been measured. You know, it's linear. So these are some of the questions I'm interested in, because I'm a solid state physicist, although I do some field theory in solid state physics. I want to know, how does this quantization vary with temperature, disorder, and other things that you could think of, okay? And these questions, unfortunately, cannot be answered by universal field theories. Okay, so for example, some of the questions I want to ask. How does the quantum Hall plateau width depend on disorder? This is gamma, by the way. Temperature and Landau level number. Do they increase? Only three possibilities, by the way: increase, decrease, and constant. Okay. So I asked, when I had this question, I mean, last 6 months I have been obsessed with integer quantum Hall effect. That's all I have been doing. I asked 10 experts. I sent email to 10 experts, all my friends, and asked them, what is the answer? This is how they distributed. 3 said increase, 3 said decrease, 3 said constant, and 1 said no idea. I'm not being facetious. This is what happened. Okay. And you know what? As I'll show you, they're all right, all correct. By the way, I have been working on it for a very long time, so that out of my respect for Rajesh, this paper was posted today. It just showed up, okay, this morning. So good. So these are the questions you're going to answer. It's a very precise experimental question. Philip Kim can do this experiment. Sit on a plateau, increase disorder, keeping everything else fixed. Increase temperature, keeping everything else fixed. What happens to the plateau width? Very well-defined question. There is no ambiguity in the question, okay? It's an experiment. And again, all those field theories, the problem is non-trivial. You know why the problem is non-trivial? Because there are too many parameters. Although it's a single particle problem, there is an interaction in it. Still, it's complicated because there's constraint of topology. First, there are 5 different variables. Usually, theoretical physicists can handle 1. Very smart theoretical physicists, much smarter than me, can handle 2. But I have been told, once you go to 3 different variables, which are all varying independent ways, very hard for us to make predictions because there are too many scales in the problem, okay? So let me tell you, let me just give you the answer first, since I may run out of time. So this paper has all the answers. Basically, what you find is that all these answers are correct. Depending on the values of disorder, temperature, cyclotron energy, all these things, the plateaus could widen, plateaus could shrink, plateaus could stay constant. All these are possible, but we precisely show the conditions where those things happen. Now, the Hamiltonian is deceptively simple. All you have is a hopping, and this is the called Pearl's substitution. This tells you there's a magnetic field going through. There's just a vector potential magnetic field through. You put it on a lattice. Electrons are hopping, and you have disorder. There's nothing else. That's all you have in the problem. Okay. That's a deceptively simple Hamiltonian, because all the other physics, like chirality, topology, are hidden as constraints, because quantum Hall effect is a non-trivial, non-perturbative effect. But fortunately, this Hamiltonian, with today's computer, we can diagonalize very accurately for very large systems, since it's a non-interacting problem, even with disorder, okay? And we did that. That's what Stuart did. So I'm going to show you some results for exact t is equal to 0 finite size calculation for a fairly large system, not as large as experimental system, but like 1,000 by 1,000, okay, which is pretty large. And these are complicated figures. What I'm showing you is the conductance. This is the longitudinal conductance as a function of Landau level filling for different disorder values. This W is disorder, okay? W is the root mean square fluctuation in that quantity V that I showed you, okay? So when the disorder is very weak, what happens when disorder is 0? When disorder is 0, you do not have quantum Hall plateau, because the chemical potential doesn't move through it. It jumps from one Landau level to another. So you have quantization, but the quantization is a set of measures 0. You cannot observe it. Now, when disorder is become slightly finite, you start seeing quantum Hall effects. So you can see this red. Now disorder is finite. You are seeing this peak, and the quantum Hall resistance is in between the peaks. So this is the lowest Landau level conductance, longitudinal conductance, second Landau level longitudinal conductance, and this is 0. Sigma xy will be quantized here. As we increase disorder, look at what is happening. The most prominent feature is the peak is going down, and peak is already shifting to the right. This shifting to the right has a name. It's called floating. The state is going up in energy. And you know what? It must, because when you go to B is equal to 0, the system should be an insulator, because we know in 2D, all systems are insulated in the presence of any disorder. So if you continue this forever, eventually this will go all the way to infinite energy, so that you recover the result of so-called orthogonal class, Gaussian orthogonal class in 2D. When the disorder is very strong, we can't even see the peak. The peak has disappeared. Okay, that's a finite size effect, by the way, but disorder has to be larger than cyclone frequency for this. So we extracted, so let's say that we can now define, because of the finite size calculation, the two definitions of quantum Hall plateau width. One is this bottom one, other is the peak to peak. One is 0 to 0, other is peak to peak. So that's what delta nu 1 and delta nu 2 are. Both of them you can see keep on going down. So I have a partial answer to the question I posed. At 0 temperature, when you increase disorder, the plateau always shrinks. At 0 temperature, nothing else happens. Plateau always shrinks when you increase disorder. Okay? Quantum Hall effect getting progressively destroyed because you have to eventually recover the orthogonal class localization at infinite disorder. Okay? So that's one answer. So at t is equal to 0, the quantum Hall plateau decreases continuously with increasing disorder with the Landau level extended state, that's the peak. Peak is where the extended states are. They're moving up in energy with increasing disorder. At least within the finite size calculation for strong disorder larger than 2 cyclotron frequency, it seems like there is a quantum Hall effect destroyed. But let me just tell you, this is a finite size effect. This is not a quantum phase transition. There's a lot of confusion on this in the literature because you can do different field theories. I mean, you can always create a field theory. If you think there is a phase transition, you can create a field theory that has the phase transition. But we are pretty convinced that this is not, this is a crossover, not a phase transition, not a quantum phase transition. So the picture, the qualitative picture is this. This is the Landau level filling. So you have quantization at these values. And this is basically disorder increasing. I'm showing it in dimension as unit of magnetic length divided by the mean free path, the mean field, mean free path. So when the disorder is very strong, very, very strong, that basically means when when you are going way up here, everything is Anderson localized. And then what you find is that as you keep on going, so all these are negative energy states, so they're localized. As you go higher and higher in magnetic field, so that you are moving to higher and higher plateau, all these states start floating up. And eventually that basically means this localization regime is taking everything over. But for you to take everything over, you have to go infinitely far in this direction. That's the zero field limit. This is the physical picture based on our work. So we also did just the conductance itself. Does it scale? And the answer, it does scale. And we did the scaling. I'm not going to go into the details. And you get an exponent, which is roughly 2.609. Theoretically, you expect it to be 5/3 because it's a percolation network with tunneling. But on field theoretic basis, you can show there'll be strong correction to scaling. And actually, Ilya Guzberg has been working on it, I think, for like 20 years or something like that, okay? And he recently wrote a paper doing very accurate scaling, and his exponent, our exponent agree. So this correction to scaling is really true. I mean, I did not quite believe it to be true, it's really true, okay? That's a minor result for us because it's already known that the exponent changes. Percolation exponent is 2.33. The correction to scaling is quite large. All right. So this is the picture based on, then we did this calculation at finite temperature also, but let me skip the finite temperature part because I'm going to talk about that in our percolation model. So that was all we could do with exact calculation. Advantage of exact calculation is it really is exact, okay? You cannot argue with that. But the disadvantage is finite size. So it's exact for whatever size you used. But experiments are basically for infinite size, Maybe where we went to 1,000 experiment, probably even the smallest experimental sample will be million. So whether you can extrapolate from that finite size to much, much larger size or not is a very difficult question. So we get some conclusions out of the finite size exact calculations, but not all conclusions. So we also did an analytical theory using a percolation model. So the percolation model is a very well-established model for quantum Hall effect. So what you assume is that disorder is very long range, like Coulomb disorder. It's varying very slowly. So your disorder correlation length is much, much larger than your magnetic length. Then what happens is the extended state we talked about, it like percolates along the equipotential line of the disorder. Semi-classical argument, very powerful theory. It has the immediate advantage that immediately gives you quantum Hall effect because that one state at the saddle point of this long-range disorder is the only percolating state. Everything else is localized in this Coulomb disorder, okay? So that one state is percolating, so it automatically gives you quantum Hall effect. And the other great advantage is that now you can do analytical work, okay? So it's an approximate theory because you have to assume that it's very long-range disorder and this percolation model applies. But once you make that assumption, which is a very reasonable assumption, by the way, our finite size calculations for short-range disorder, okay? And this is for long-range disorder. So we can do real theory, meaning we can do analytical work. And what we find is that now you can include finite temperature without any problem. It doesn't have to be at 0 temperature because, you know, we can just put finite temperature in this model. So the summary is that the thing that we're interested in is that the correction to the quantization, right? So at t is equal to 0, Chern-Simons theory tells us that the plateau is of size 1. The whole thing is plateau. There is nothing else. Because Chern-Simons theory, the field theory doesn't have anything else. So at t is equal to 0, the physics is only physics of plateau. There is nothing else for infinitesimal disorder. Yeah. So we said the correction, let's say call it 1 minus delta nu p. We're interested in delta nu p. Analytically, you can calculate in various asymptotic limit. This delta nu p goes as temperature divided by disorder when disorder is larger than temperature but smaller than cyclotron energy. But if disorder is larger than even cyclotron energy, then it goes as T over H bar omega C. And we have analytical results. You should look at the paper for many other limits also, because that's the advantage of it. And so what you can say, you may ask, but what happens if T is larger than everything? What's T is the largest thing? Well, when T is the largest quantity, you have no quantum Hall effect. All quantum Hall effect goes away, as Philip Kim knows very well. You go to high temperature, everything goes away, okay? So this is what it looks like. So what it looks like is this delta nu, the correction from 1, it first, with increasing disorder, I'm sitting at some fixed temperature, T, I'm increasing disorder. At first, it actually expands. Because why does it expand? Because disorder is broadening the density of states, and this broadening of density of states is counterbalancing the effect of temperature. So at first, it expands. Then it reaches a kind of constant regime. Then when you go to still higher disorder, it starts coming down. Now you can see this part is not there at t is equal to 0. T is equal to 0, you have only this part. It all shrinks over here, and you have only this part. So everything is consistent, okay? So our t is equal to 0 theory, which says plateau only shrinks, is completely consistent with this analytical picture. Plateau at first grows, then shrinks, because at t is equal to 0, you have only this piece. So in some sense, my 10 friends all gave right answers. It expands, it shrinks, it may even remain constant, and even no idea is the correct answer also, because it depends on all the parameters. So, since time is running out and I have too many parameters here, and since the paper is already posted, these are the actual explicit calculations. You can see explicit calculation is showing exactly what I told you. This is this part, this is this constant part, this is this part rising. So what I'm trying to say, this analytical work is supported by numerical calculations based on this analytical model. These are not finite size calculations. These are just doing integrals numerically. And this is experiment. Experiment actually sees exactly, and these are all experiment 80s. Nobody works on integer quantum Hall effect after 1985. So, when I tried asking people, all the people have retired. I mean, Horst, Sarma, Dan Sui have retired. I didn't want to bother Klaus. So we had to find these papers. You can see it grows as this is disorder. It grows at first, then it shrinks, exactly as our theory calculations predict. We have a very complete theory, but I think I made my point. This is also actual theory. This is what it looks like at 0 temperature. Now, you go to finite temperature, the plateaus start going down. This is finite temperature, okay? Now, add disorder, and this is disorder and temperature. I'm not going to discuss these figures in great details because it's summarized over here. I already told you what happens, okay? Here are some experimental results. Let me show you some experimental results, okay? This is the first verification of von Klitzing's measurement by Sui and Sarma and Sui, okay? It's in PhysRev and in gallium arsenide. It's a very nice paper. And one thing they noticed right away, and they made a very big deal in this paper, that they expected, because in semiconductor physics, good things happen only when you have a better quality sample. That's why Philip Kim was emphasizing how great his graphene samples are. That's why Arindam Ghosh was emphasizing how his graphene samples were. Here, on the other hand, they noted this integer quantum Hall effect is better when the sample is worse. Already in this paper, they talk about it. A strange thing that the plateau becomes wider as the mobility goes down, okay? And they actually make a big deal of it. Everybody forgot about this paper. I mean, and they didn't have a picture that. Then there's a paper by Klaus von Klitzing in 1990 showing exactly the same thing, that this the lower mobility sample, the top one, has a much wider plateau than the higher mobility sample, okay? But this is very recent work by Gabor Sati, very high mobility devices, 25 million. He's seeing all kind of fancy things. And you know then what he finds? He finds that the integer quantum Hall effect doesn't form there. It's very bad. Integer quantum Hall effect is very bad, 50 millikelvin. Then he makes up all kinds of stories about, oh, it must be Wigner crystal, competing phase transition. And then he goes to very low temperature, 6 millikelvin, the plateau becomes perfect. It's an amazing result. If you have a very high mobility device, you will not see integer quantum Hall effect at all. If your sample is perfect, the samples that Philip was talking about, or even better, there'll be no integer quantum Hall effect. You have to go to very, very low temperatures to see integer quantum. And this is because of physics I was talking about, okay? So this is, I'll quote from Marv Cage, who was in charge of resistance standardness. He retired now. In a very early paper, in a book in 1987, he already said, widths decrease with increasing T. They also decrease with increasing mobility. Widths disappear at high mobilities, disappear at high mobilities. Nobody paid attention to this thing. I discovered all these things after we did our work. I was literally looking for experimental support. These are all, nobody worked on it after 1987, okay? So we explain all of this. Universal Chern-Simons theory cannot, because that theory is too universal. Integer quantum Hall effect difficult to achieve in better samples. In fact, impossible to achieve in samples where eventual topological quantum computer will work, okay? All right, now I'm going to give you a preview of what my friend Sankar will tell you. You should ask a question. Well, if it's topology, why do I need a high magnetic field and all this, thing? I mean, why can't zero field seem? Sorry, it's just topology, right? Topology has nothing to do. I mean, magnetic field may produce topology by producing breaking time reversal invariance and producing chirality, and people ask that question: can integer quantum Hall effect occur at b is equal to 0 or in lattice system? The answer is yes. All you need is topology and spontaneous breaking of time reversal invariance. Now, this idea actually was around, 4 groups wrote papers. I don't know exactly how this happened. You're not talking to each other. 4 groups wrote papers together in 2010 or 11. I'll just show you in our work, but there are 3 other papers, all different, all distinct. And we showed that if you take a really crazy lattice, I mean, we knew what you're looking for, right? We're looking for a Chern number in the end, okay? So you can create a lattice where the band is completely flat, and you get a Chern number because of breaking off time reversal invariance spontaneously because of ferromagnetism, because that happens all the time in solid state system, that you can have a spontaneous breaking of time reversal invariance. And, and we even went ahead and said that once you have integer quantum Hall effect, you'll have fractional quantum Hall effect also. By the way, I never thought these predictions have anything to do with reality. I told Keynes, these are very nice theories, but I'm not interested in them because nobody will ever see it. The reason is that the model that we have, it doesn't occur in nature. It's kind of a modified Lieb lattice, very complicated hopping and so on. But in any case, I'm not going to show you the results. I'm hoping Senthilud. This has all been seen. Last 2 years have been amazing in condensed matter physics. Right and left, people are seeing zero field quantum Hall effect, zero field fractional quantum Hall effect. And non-abelian set has not been seen yet. It will be seen. Because all you need is topology and breaking up time reversal invariance, or maybe become spatial inversion, which gives you a Chern number. And Chern number, once you have a Chern number, everything else will follow. And that's about it. I'm not going to describe this paper. I don't think this is necessary. So let me just conclude by telling you that topology and quantum mechanics will continue the synergy. Now that you know they're one and together, this synergy will continue forever, I think. I think they'll become the same subject. Like matrices and quantum mechanics became the same subject because of Heisenberg. Matrices were a very obscure object, even among mathematicians in 1925. But now it's a common thing. Same thing will happen. And I assure it also lead to the first practical fully quantum machine. Maybe Pedram has left. I hope he has left. Oh, you are here. I was hoping you will do the usual corporate thing, give your talk and leave. But in any case, I think topological quantum computer will be the really feasible practical quantum computer. I'm not saying in a facetious, my definition of quantum computer is a bit different from his. I want a computer that can factorize 1,000-digit number. So that means you need 10 billion qubits. So why, various reasons. So 1 million is not enough. I don't see anything other than semiconductor that can be scaled up. This is just an engineering manufacturing question. So I think that now that is topological order, a much more complicated object than topological phase. I'll leave it to a much smarter colleague of mine, Senthil, to talk about topological order, and I'll stop here. Thank you very much.
Thank you very much for a very nice talk. We have time for maybe a couple of questions. Please raise your hand on the.
Looked at the disorder. What about the system size? Can you make the system size arbitrarily small or large to get the?
Yeah, so we have some other system size results also. System size will have the same thing. As I showed you, if you can do the measurements in a small system size, you will then conclude disorder destroys quantum Hall effect. And that's true. I showed you results, mark gauges, not as small as our system size. So basic answer is that when the system size is finite, and even if it's 10 times, I mean, our thing is like 200 times the magnetic length. Already quantum Hall effect is affected. Okay, so yeah, system size is rather trivial to do. I didn't emphasize it, and it's consistent with experiment. Okay.
Any other questions? Yeah.
So when you said analytics, is it like a John Chalker kind of network model?
No, it's the same thing. What Chalker did, he took the percolation model, which predates him. He took the percolation model, put it on a lattice, and did a full quantum mechanical theory. Okay, but what I'm saying, if you're interested just in quantum Hall, because he was interested in, I mean, theorists are obsessed with plateau-to-plateau transition, because thanks to my friends who research there, quantum phase transition is a big theme in our subject. So people are interested in the quantum phase transition, and that comes out naturally. For what I'm interested in, I don't have to go the full network model. I can have a more primitive model underlying just the percolation model, but it's the same thing. If I put in a lattice, do a full quantum mechanical calculation, that's when it's called network model. And in fact, as you know, there is this exact one state that's extended. It's the same thing. But percolation model is broader.
Because you can write transfer matrix and go to ASLA system.
That's what I meant by analytical. That's exactly what I meant.
Okay.
That is exactly what I meant. The system size is not a problem anymore. That's precisely what I meant.
Okay. Thank you.
All right, so let's thank the speaker again.